when ultra-class haul trucks like the Belaz 75710 began carrying up to 450 metric tons in a single load, did mining cross a point of no return in the pursuit of scale? In 1957, Berliet introduced the T100 near Lyon, a machine built for the Sahara's extremes, not for show. Measuring over 15 meters long and nearly 5 meters wide, the T100 was the largest truck of its time. Its two 29.6-liter Cummins 512 diesel engines produced 700 horsepower, driving a semi-automatic hydraulic transmission and powering all 6 wheels. Capable of hauling 30 metric tons, the T100 set a new benchmark for what a truck could achieve in the harshest conditions. Only 4 units were ever built, but their influence was immediate and far-reaching. Mining and oil engineers from North America, Australia, the Soviet Union, the Middle East, and South America studied the T100's scale and engineering, recognizing a solution to the growing challenge of remote resource extraction. Within a few years, the concept of the giant haul truck took root across 5 continents. Canadian mines tested heavy diesel rigs for copper, while Chilean engineers sought ways to move more ore as grades declined. Australia's iron ore industry, facing vast distances, saw the value in fewer, larger machines. The Soviet Union began laying the foundation for its own massive trucks, and Middle Eastern oil fields adopted oversized multi-axle vehicles to handle rough terrain. The T100's legacy was not about spectacle, but about necessity. As mineral grades fell and costs rose, size became a strategy for survival, setting the stage for the next leap in drivetrain innovation. By the late 20th century, the brute force approach of early giants like the T100 had reached its limit. The next leap came not from bigger engines, but from a fundamental rethink of how power moved from diesel to wheels. Engineers in North America, Japan, and the former Soviet Union found answers in the diesel-electric drivetrain, a system that replaced heavy mechanical gearboxes with generator-fed electric wheel drives. This shift allowed for continuous, precisely controlled torque at low speeds, essential for hauling 300 tons or more up steep, uneven grades. Unlike mechanical transmissions, which strained under fluctuating loads, the new electric systems delivered instant response and smoothed out stress spikes that once cracked frames and shortened component life. White papers from the era documented how electric drives cut peak mechanical stress by up to 30%, extending service intervals and reducing costly downtime. The physics behind this was straightforward. With a diesel engine running at its most efficient speed, electricity could be metered to each wheel independently. The result was a truck that could crawl up a 10% incline with a full load, never stalling or burning out a clutch. For mines facing deeper pits and declining ore grades, this meant one machine could now do the work of 3, with less wear and lower risk of catastrophic failure. The collective efforts of drivetrain pioneers, engineers at Komatsu, Caterpillar, Bell AZ, and Liebherr turned the diesel-electric concept from a laboratory experiment into a practical solution for the world's largest mines. Their designs laid the foundation for the ultra-class platforms that followed, making controllable torque and stress reduction the twin pillars of modern haul truck engineering. The era of generator-fed wheel drives was not just a technical milestone, it was the enabler that made the ultra-scale practical, setting up the divergent design philosophies that would define the next generation of mining trucks. In the world of ultra-class haul trucks, 2 design philosophies stand out, each shaped by the same relentless demand: move more material with fewer machines. On one side, Komatsu's 980E5 targets the 363-ton payload class, drawing on a legacy of diesel-electric refinement. Its single 18-cylinder, Tier 4 diesel engine generates 3,500 horsepower, driving a fully integrated alternating current system. Komatsu's approach centers on digital control. More than 200 sensors monitor every parameter in real time, from axle temperatures to torque loads. The truck's telematics suite, CommVision, offers 360-degree situational awareness and predictive maintenance, and an optional autonomous haulage system can run the truck without a human operator in the cab. Every element, from the climate-controlled ROPS-certified cabin to the collision avoidance radar, is designed for reliability and data-driven efficiency. Contrast this with the Bell AZ 75710, which pushes the boundaries further at 450 tons and emphasizes raw capacity. Instead of one massive engine, Bell AZ employs two 65-liter V16 diesels, each delivering 2,300 horsepower. These engines feed four independent alternating current traction motors through a Siemens electric transmission. The dual engine layout is not just about brute force, it allows the truck to run on a single engine when lightly loaded, saving fuel and extending service intervals. 8 giant Michelin tires, each nearly 4 meters tall, distribute the weight across a wider footprint. Rather than emphasizing digital telematics, Bell AZ leans on mechanical redundancy and the ability to maintain uptime, even if one engine or drive module fails. The focus is on maximizing payload per trip, with regenerative braking and dynamic dumping systems shaving minutes off each haul cycle. Both platforms chase the same goal: drive cost per ton down in an era of declining ore grades and rising operational costs. Yet their engineering choices reveal different answers to the same equation. Komatsu bets on information and automation. Bell AZ wagers on raw capacity and mechanical resilience. The result is a practical demonstration of how physics, economics, and legacy engineering converge at the edge of what is possible in modern mining. Moving a 420-ton haul truck up a 5% grade is not a feat of brute force. It is an exercise in physics and precision. Every element of the diesel-electric drivetrain is engineered to deliver just enough tractive effort, measured in kilonewtons, to overcome the pull of gravity and the drag of rough ground. For a truck loaded with 420 metric tons, the math is unforgiving. Gravity alone demands about 206 kilonewtons just to keep the truck moving uphill. Add the rolling resistance from 8 massive tires, each nearly 4 meters tall, and the total climbs to roughly 235 kilonewtons. That is the threshold if the truck cannot deliver this force at the wheels it stalls on the ramp, no matter how powerful the engine claims to be. The diesel-electric system solves this with a chain of components. A high-speed diesel engine spins a generator, which feeds power through an inverter to electric traction motors mounted at each axle. Unlike mechanical transmissions, which struggle to deliver steady torque at low speeds, the electric motors provide continuous, controllable force from a standstill. At a crawl just under 3 kilometers per hour, the system needs to sustain about 653 kilowatts of wheel power to keep the fully loaded truck moving up that grade. This figure comes straight from manufacturer data sheets. BLAZ, Komatsu, and Caterpillar all specify wheel power in the 620 to 660 kilowatt range for their ultra-class models at 5% grades. The control advantage is just as important as the raw numbers. Electric drives meter torque to each wheel independently, smoothing out the stress that once cracked frames and shredded gearboxes. Operators can modulate power in real time, matching the exact resistance of each haul road segment. The result is not just the ability to move enormous loads, but to do so reliably, day after day, without burning out clutches or risking catastrophic failure. This is the physical logic that underpins the economic case for ultra-class trucks. The right amount of torque delivered exactly where and when it is needed turns the physics of mass and incline into a manageable, repeatable process. Cost engineers in mining do not spend much time marveling at the size of a truck. They run the numbers. At a typical open-pit operation moving 450,000 tons per year, every dollar spent must return more metal from ever thinner ore. The arithmetic is unforgiving. When ore grades fall, as they have in Chile and Australia, the volume of rock that must be moved climbs sharply. The only way to keep cost per ton from spiraling out of control is to move more material with fewer machines. That is where the ultra-class haul truck enters the equation. With annual operating costs around $2.5 million and a capital charge spread over 15 years, a 450-ton truck like the Bell AZ 75710 delivers a cost per ton of about $6.70. This figure is not a marketing slogan. It is the result of life cycle cost models that account for fuel, chassis, maintenance, and depreciation, all divided by the actual tonnage moved. Mines that once relied on 30 trucks rated at 100 tons each now get the same throughput from a dozen ultra-class haulers, cutting operator headcount and slashing fuel use per ton. As ore grades keep dropping, the economic tipping point for ultra-class trucks becomes impossible to ignore. The physics of moving rock and the arithmetic of cost per ton converge on the same answer. Bigger is not just better, it is necessary. Ultra-class haul trucks face steep costs before moving a single load. Tires alone can run $500,000 per set, each one nearly 4 meters tall and weighing over 5 tons. Mines keep full replacement sets on site, a hedge against supply shocks that have grounded entire fleets. When a tire fails, crews use hydraulic lifts and tools designed for components heavier than most cars. Assembly is a feat in itself. Trucks like the Bell AZ 75710 arrive in modular pieces, shipped across continents, and assembled over weeks. Frames are built from high-strength alloy steel, engineered to handle relentless flex and vibration. Metallurgists use finite element analysis to spot weak points, while maintenance teams monitor weld seams for early signs of fatigue. Axle loads demand careful balance. 8 wheels spread the weight, protecting haul roads but exposing more parts to wear. Hundreds of sensors track tire pressure and frame strain, with predictive algorithms flagging trouble before breakdowns hit. Maintenance crews and supervisors juggle spares, labor, and digital oversight, always chasing reliability in a world where every fix carries its own price. Today, ultra-class trucks move nearly 45% of the world's mined material, shaping global supply chains and energy demand in real time. Their scale isn't spectacle, it's infrastructure. As industry pushes physical and economic limits, the question is what we build on top. Subscribe to join the ongoing investigation into the systems beneath our world.